Okay, we're back. This is AP Physics 1, check-in number 10. This one has to do with simple harmonic motion, which in a lot of cases, you know, in class we refer to as SHM, simple harmonic motion. Okay. First situation, you have a graph you're going to analyze. This is a graph of displacement in centimeters versus time in seconds. And it asks you to write an equation for the displacement of the object as a function of time. Well, from this, what do I know? I know my amplitude is 10 centimeters, which is 0.1 meters. And what else can I find? I think I can find, because we're graphing it as a function of time, the time it takes to go from the peak to peak is the period, and that appears to take 2 seconds on the graph. So if I go back to my original simple harmonic motion equation, which would be A cosine omega t, the displacement should go by that. And so if we put in some variables, we should have 0.1, and that's going to be in centimeters, times the cosine of omega t, but omega we should have said was 2 pi over t, so that's 2 pi divided by 2 seconds, which was pi itself. So maybe we could call pi 3.14, and that's going to give cosine of 3.14 t. Make sense? Okay. Write down an equation for the velocity. Well, the velocity, if you're using calculus, you might take the derivative, but instead we just say in class it's just minus a omega, and then that will give you the derivative of cosine as sine, but you can just write it as sine omega t. Substituting, this is going to be minus 0.10. Omega is the 3.14, and then you'll have the sine of 3.14 times t. And so you put those together, 3.1, how about 0.314 sine of 3.14 t. You could have left it in terms of pi, but if you're one that likes decimal answers, you get it. What is the maximum velocity? The maximum velocity is when the sine becomes a 1. You know how sine goes from -1 to +1, so it's either positive or -1. That would mean that whatever's in the part out front of it is going to be the maximum value. So that's going to be when you have a times omega, plus or minus. And so in that case, that would be 0.314 meters per second would be the case where we would have the maximum amount of velocity that particle in simple harmonic motion would have. Okay? So that's where we go from there. All right. Next, we have an example of a pendulum on another planet, and it asks you the question, what is the gravitational field strength on that planet? Gravitational field strength is the same as the g value, or the acceleration, what we normally probably call the acceleration due to gravity. Okay? So you know that for a pendulum, you've got the equation 2 pi square root of L over G is the equation. And they give you in this problem on another planet, the period is 3.8 seconds, and the length of the pendulum is 1.5 meters. And so we want to know, what is the gravitational field strength? What is G? That's what we're looking for. So we probably have to square both sides of this equation. T squared is 4 pi squared L over G, and solve for G. G is then equal to 4 pi squared, if we kind of cross multiply, L over T squared. And so we could put in 4 pi squared, L is 1.5 meters, and T is 3.8 seconds, and we're going to square it. So you put in those numbers, and you get that G, the new G value, you might want to call it prime now because it's not on the Earth, is 15 0.6 meters per second squared, whereas on our planet it's 9.8. Here on this planet it's 15.6. Okay, pretty straightforward situation. The last one is just taking a look conceptually at 3 different ways we can look at simple harmonic motion. Probably in class you talked about an object in simple harmonic motion, the thing swings back and forth, or a mass vertically on a spring, swinging up and down, or a mass connected to a spring sliding back and forth horizontally. Those are 3 examples of simple harmonic motion. And it says, what allows these cases to move with oscillatory motion? What would causing that? And just to remind ourselves, we said that in class that it had to have a restoring force that put it back to the equilibrium position. For the pendulum would be right here in the middle. If it swings back and forth wherever the equilibrium point here, or maybe if it swings back and forth here, it's always going to try to, the spring or whatever's applying the restoring force, which we'll get back to for pendulum in just a second, the spring is always trying to get it back to this equilibrium position, either horizontally or vertically. For the simple pendulum, it's got gravity, but it's really the component that pulls it to the center, which we might call like the x component of gravity, that gives us the restoring force. So it's either in terms of a pendulum, that x component, or it's going to be the spring force that is going to get the job done. This might be like an mg sine theta, where theta has to do with the angle of deviation from vertical. And this one is going to be like minus kx. These are actually both minus because they're always taking it back to equilibrium. So that's what the purpose of that question is for you to analyze the restoring force that gets you back to that position. The last question says, if you vary the mass, which ones of these have period change? Well, it turns out that the period involves the mass for one of these 2 cases. For a pendulum, it's L over G, but for a spring, it's 2 pi times the square root of m over k. So for the mass connected to a spring, the period is going to change because of the fact that you have a mass change that changes the period. But since the pendulum doesn't have the mass in it, it wouldn't matter what the mass was. You'd have the same period. So for the varying of the mass, that would be changing the period for both these 2 cases, mass on the spring, but not for the pendulum. Okay. I hope that was useful. That's our 10th case there we did here for these check-ins. So I hope that was useful, and we'll talk to you later. Stay safe.